So for today, I'm going to be talking to you about the new fault statistics tool that's been added in Petrosys PRO version 2023.1. And now this has been added to our mapping functionality, and it is included along with your maintenance renewal for the ongoing maintenance of Petrosys PRO and Petrosys support. Now, before I get into the details of how the tool works, I want to add some context as to why this tool was developed. Fault patterns essentially play a large role in how we perceive and the distribution of sediments and also the migration of fluids through the subsurface. Now, this is critical to petroleum, geothermal, and CCS industries. Fault connectivity can also define the size, the shape, and the internal compartmentalization of a structural trap. And the assessment of fault structures can then help geoscientists identify the location of these traps and also the potential for fluid leakage through spill point zones. When you map out displacement patterns showing the amount of throw, heave, or displacement that's occurred along a fault, that can essentially be used as a QC for the structural map. Those displacement patterns should really be consistent with the fault system that you've interpreted, and also the long-established length displacement ratios that are published in structural geology literature. The displacement color maps as well that we can now support in Petrosys PRO can also give an indication on the distribution of strain across your system and give a quick pass indication of the structural history. So with that being said, we gathered a range of customer feedback across the region, and it led to us essentially developing a toolkit that allows users to refine their structural maps with this fault statistics tool. Some of the key pinpoints that users picked up on was the ability to color code and essentially thematically map your faults based on their displacement amount, being able to dynamically select those faults in the map view and compare them against tabular data and plotted data, and essentially it allows users to then go on and visualize any mapping areas that they can then refine through using either our spatial editor, which hopefully you're very familiar with, is a really useful tool for editing faults, editing grids, and also the faults that are embedded with grids. And you can also then go back as well and change the gridding algorithms if you want to try and assess the influence of parameters such as adding in a clipping distance to the geometry of your faults. So after gathering that feedback, we essentially developed this fault statistics tool. Now, this tool, as I mentioned, is part of the mapping canvas of Petrosys PRO. And when opened, it will essentially open a panel to the right-hand side of your mapping canvas, where it will display a throw profile along with tabular data showing the maximum throw, the length, the azimuth, and the strike of each fault included within your selected file. It will then also include functionality that will allow you to thematically map that data, so you can thematically map the data on the map canvas itself. And then the final thing to note is some of the editing functionality. So you will now be able to smooth out if you see any kind of sharp changes in throw across your throw profile plots. You can edit that by moving the nodes within the plot. So I'm going to go into a bit of this in a bit more detail. So first of all, to mention the throw profile. So this is the profile that you'll see at the top of the tool. And that essentially will display across the length of a fault the throw experienced along the length. It allows you to essentially assess the validity of a subsurface map through the assessment of a single fault or a multiple faults. So you can see here that within this table here, you can turn the display of faults on and off. In this instance, we're just displaying one fault, but you can also combine several different faults at once or show the entire kind of X number of faults within that file. It then gives you an indication of how these faults relate to one another. You may have large populations of faults which are in excess of 5,000 meters length, and you may also have a population of much smaller faults that are below 1 kilometer length. As I mentioned, it's also possible to thematically map those fault statistics that are now calculated for each of those faults. So the first thing you can display is you can choose to display the throw distribution by mapping the throw gradient across the length of the fault. That will essentially allow you to choose what color gradient you want to define, and then it allows you to quickly identify high slip zones. And this, of course, has implications for your lithological juxtapositions. So as you can see in this image down here, we've got a zone around here where this fault has experienced quite a high vertical displacement. And comparing that to the rest of the data set, you can see here some of these north-south trending faults. They don't experience nearly as high a throw as shown in this region down here. On top of that, there's also another slightly different tool which allows you to analyze the maximum throw, the fault length, the fault strike, and also the fault azimuth. So what that will do is that will assign a color to a single color to each of your faults, showing that attribute. Now, within that, and I'll show this in a demo in a second, you're essentially using the functionality that's available within the Display GIS tool. So you have the option to display a gradient, or you can display within fixed color intervals and so on. So you have a fair bit of flexibility around there. On top of that, you also have access to the filtering and the annotation tools. So that can be used potentially if you want to really highlight in your map some of the faults that are displaying a throw over a set amount, or you could potentially highlight faults that are trending in a particular orientation. Now, as I mentioned, we also have this capability within the plot itself that allows you to edit the geometry of the fault. So take this example here where we've got this throw profile and we've got a very sharp and sudden change within the fault. What you could do, you could combine this tool with the 3D viewer to check whether this is a realistic example of a fault geometry. In this particular instance, we've seemed to have gridded up a erroneous data point. So what we could do is we could essentially select these nodes here and pull them up to smooth out the throw, and then you can save those edits and save them essentially back into a secondary fault file. Once you've done that, you could then potentially push that fault file back into your gridding tool, and then use the Z values from that file to better create your output grid. Alternatively, what you could do is, if you notice this within the throw profile itself, you could use the spatial editor to open your grid within the spatial editor and smooth out those areas where you're seeing these large jumps in throw. On top of that, as I mentioned and showed earlier, so the fault statistics tool will generate a tabular list of each of your faults. And within that, it will calculate the maximum throw, length, azimuth, and strike for each of those faults. You can take this data and you can cross-plot this data, and I'll show you how to do that in a second, which means that you can then analyze the relationship between features such as your fault maximum throw and your fault length. Or alternatively, you can plot your azimuths against your throws and just see whether you can draw out key populations of faults. It also allows you to identify outliers, so areas where your fault is potentially not fitting in well with this linear trend here. So in this instance here, some of these faults up here, we may identify a case where this single fault, which is at this specific length, has actually over-calculated a maximum throw. In other cases, in opposing cases, you could potentially identify cases where you may actually want to segment your fault up into and split it up into smaller items, which means that that then has implications for spill point analysis. So here's just another example of that data being plotted, where you're plotting the azimuth versus the maximum throw, and you can clearly see the 4 distinct populations within your area of interest. So this tool works with fault polygon files from Petrosys Pro, and it also works with fault polygons that are stored in third-party applications. So we support those applications such as Petrel and Kingdom and Dug Insight and so on. You can see the full list at the top here. We also support the calculation of fault statistics from Petrosys Pro grids. So any grid files that contain embedded fault polygons, we can extract the statistics of those. The key thing is that those faults must have, essentially the fault vertices must contain Z values. If they don't, you'll essentially receive an error warning saying that the tool's not able to plot that data. So what you really need to do is make sure that that data is contains that information and is also topologically sound. Another instance where it's not going to plot that information is where you may have faults that are self-intersecting or faults that are missing apex values. So I'll demonstrate this in a second, and I'll show you how you can go about and fix this so you have a complete data set where all those faults are being plotted and thematically mapped. Now, one last thing to mention, so within these plots, the throw profile plots that are generated, you can export that data to Excel. You can also export it to a PDF, a raster image, or directly into your PowerPoint presentation. So in this instance here, I am displaying a Petrosys fault file. And what you'll notice is there's an icon up here which will open up the fault statistics window. But what you need to do to automatically populate this is if you just select that fault layer, right-click and select fault statistics. It will then automatically calculate the throw, length, azimuth, and strike for each of those faults, and it will plot that data in the throw profile plot. Now, one thing to mention is this is all dynamically interactive. So if I select a row within my table, you should hopefully see that that fault is being highlighted within the map canvas view here. And what you should also see is within the plot, it's going to display each of the nodes, essentially, of the fault, which you can then move and edit if you want to. What I would also like to show is that this table, you can sort this table. So if you select the header columns up here, you can sort that by maximum throw. You can see here that we're listing now the fault which is showing the greatest throw across your data set, and that fault is then being highlighted within the map view itself here. And you can do so with each of the columns. Now, as I mentioned earlier, you'll see that I'm plotting data from most of my faults, but the very first fault at the top here has an error against it, saying fault error. Now, if you select this, down here in the toolbox, we've tried to add explanations as to why the tool is failing to plot that. But some of the most common issues are where essentially the fault polygon is self-intersecting, or where it's missing Z values. So to fix that, what I'll just do as well, just to show you, is I'll just turn off all of my faults and I'll turn this one on. You can see that because of that error, it's not plotting anything. So what I need to do in this instance is we have a shortcut icon down here to the spatial editor. So I'll just select that. And then I will zoom in to this fault here. And because it said it's got a problem with the fault self-intersecting itself, I know this is probably going to arise around about here, where we're essentially seeing a collapse down to a heave of 0. If I select the fault and turn on the fault vertices, you can see here that in all likelihood, my nodes, fault vertices that represent the top of my fault versus the base of my fault have essentially been overlapped. So what I'll do is I'll make sure I pull out the fault ever so slightly so the base is on the hand side, and then if I click save to that, let's hope this works. There we go. So now you can see that it's now able to then plot that throw profile for that fault. So that's just something to be aware of, because it may be something that you encounter within your data set. Now, what I'll go back to is I'll just turn all my faults back on again. And let me click select all. Now, as you can see, we've got some of our throw range essentially goes from close to 200 meters to down to almost negative 75. So where it goes into the negative realm, that means our hanging wall has been thrusted above our footwall. This sometimes quite commonly happens where you've got very small faults, where the seismic data is essentially picking up areas where your hanging wall has essentially been thrusted up ever so slightly. So that's not something to worry about too much when you've got this in small faults. But if you have this in much larger faults, it may be something that you want to go back to and investigate. Now, the next thing I want to show is these two controls down here. So if I select this control, it is called display throw gradient. What it will do is it will automatically open up this window, which allows you to assign the gradient, the color gradient that you want to apply to show the throw. So I'll just click OK to that. And then that essentially adds a temporary layer to my display list. So I'm going to pull this up to the top of my display list, and then you can see you essentially now have your data set color mapped to show the throw distribution. I'll just turn off the original layer down here. Now, one thing to bear in mind is if I zoom in, you can see areas where essentially no color fill is being applied. Now, this essentially works, this functionality works in a similar way to the gridding algorithms that we use for creating and color mapping our grids. So it has to use a cell size of a defined XY length to essentially calculate the throws across our faults. If you want to fill in these gaps here, all you need to do is go to your settings panel, go to the layers tab, You see here by default the X and Y cell size is 100 meters. If I change that to 20 meters, I'll click close, and then I'll just turn that layer off and back on again. And you can see when I turn it back on, it will take a little bit longer to display that data, just because it's now using a smaller cell size. But when I zoom in, you can see that the majority of those gaps are now filled in, and you get a cleaner output. The next icon or functionality that I want to show you is the display thematic options. So what this tool does is it takes the data shown in this table here, and it will allow you to thematically map that. And if I click on that now, it will open up this window here. And for those of you who are familiar with the Display GIS tool, you should hopefully see that it's actually very, very similar. So you get the option to display annotations, and I'll come back to that. You get the option to filter the output layer. So if I want to display just faults that have a throw above, say, 150 meters, I can do so. And then we have the thematic mapping options, which gives you a large range of flexibility. So in this instance, I'm going to turn on display enable thematic. I'll choose series gradient. Then I'll just use the same color gradient. You'll see that I'm mapping my maximum throw. And I'll click apply to that. And again, I'll just drag this layer up to the top there. And what it's done there is essentially applying a single color to each of my faults, depending on what the maximum throw is for each of these layers. Now, if I go back to the display annotation tab, I can choose to display that as a label. So I've added that in there. And I can also choose to filter. If I want to, I could go back here and say, okay, now I want to display or color map the length of my faults. And in this instance, I'll choose a different gradient. Let's click apply. You can see there that the faults with a richer blue are essentially the longer faults. What I could also do is choose to display my fault azimuth. And in this instance, I might want to change the thematic mapping style to the range color option here. And that essentially allows me, you can see I've already pre-populated this where I've said my minimum value is 0, my maximum is, that should be, 359 actually. And then you can also define an interval value. So I could choose an interval of, say, 20. Let's click apply. I realised why that's not worked, is I just need to click generate. Then I click apply, and it will show the azimuth color mapped along each of my faults, although I'd probably want to change the color values there so we see something that's more easy to visually interpret. If I want to, I could massively increase my interval and click generate and then apply. You can see there from just using that interval there that the majority of my faults are dipping towards the east-southeast orientation. So when you have larger, more regional maps and you maybe want to highlight this out, the general trend in dip direction, you can do so using these tools here. I'll just click OK to that. And then for the final thing that I was just wanting to show for today is I'm going to zone in on one of my faults, and the faults that I'm going to look at more closely is this fault here, fault 16. So what I'm just going to do is I'll just click select none, and then I'll turn that fault back on. You can see that this fault, there's a real sharp change in throw. And that, if I just turn this layer and this layer off, and I'll just go back to my original data set, I select that layer, it refers to this fault down here. It's probably likely we're looking at around about the center of the fault, that's occurring around this region down here. So you see this sharp change in throw. And what I can do is if I select that, let me just make sure the node's selected there, and I hover over this node, I can essentially pull this back up to here. And then once I've done that, I can save that out to a new fault file. So what I'll do is, because the tool works by selection based, I'm just going to make sure that all of my faults are selected again. And then I'm going to click save. And then you can choose to create a brand new fault file. You can choose to define the type of fault file, whether it's polyline or centerline. And then once you've saved that, you can click OK. And then that data will be saved out to a new file, which you can then use to rerun a gridding process, for example, or for then pushing into another third-party application. So that really summarizes the key functionality within this new tool. Thank you very much for attending and for listening along. If you have any questions about this functionality, please do let us know. You can email support@petrosys.com.au, or for more information about Petrosys Pro in general, please feel free to email or contact info@petrosys.com.au. Thank you very much.